This week, implementation. So, talking about thinking about the whole process of implementing software systems, with a particular emphasis, obviously, in this case, on databases. But as with much of the design content of this module, it also relates to the programming design and things like that in next semester. So what we're going to do is, it's a bit of a sort of collection of things together. First of all, revisit the design methodologies, which we've touched on earlier in the module, particularly in relation. We met the waterfall model really, really quickly. We're going to see some other, briefly, very touch on other design methodologies. Just a tiny bit on personnel, people. After all, when you're the very first, what is a GIS? What is a GIS? It's a technology, data, people, so personnel roles. And then a little bit finally on what I'd call database efficiency, things about getting your database working in a suitably fast and being suitably configured so that it meets the needs of the system, and including we'll look briefly at distributed databases, what they are, basically just explain what they are, and of course distribution potentially is one way of increasing volume throughput and things like that. Okay, so first of all, I thought just a quick, this fly is so annoying, contrast between the design and implementation. So we've already had couple of lectures on design. So what's implementation? Well, implementation is just a sort of the bigger picture, so to speak. So design, kind of defined as a plan or a schema that specifies the look, functionings, or workings of something in the world. And it could be obviously we're interested in GIS computer systems, databases. It could be the design of a database, the design of an interface, a spatial interface, anything like that. But it also, of course, works for things like building diagrams, clothing diagrams, and everything else. And it is something that you do before you build something. It's also something that goes on while the process of building goes on, but it's something that primarily happens before. And implementation, design is part of implementation. Implementation being the full process from the initial idea. Wouldn't something like this be useful or interesting, to actually the end product at the end of the day? And it includes the execution of the design. So that's the difference between implementation and design. So we've already covered this before, but it's just to put things in context. So the ideas of conceptual design, logical design, and physical design come from the system engineering literature. I must say, I find what the difference between system engineering and other design disciplines is, I can be a bit fuzzy from an outsider, but it comes from systems engineering. So we have the idea of the conceptual design, the high-level business functions and requirements of the system. You start with an abstract model, and then you move to a logical model, which sort of fills in the gaps and produces you a system on paper. Then once you have a fully working system on paper, then you go into the physical design, which implements the logical design within a particular software system. And I overlaid that onto these various modeling steps onto the overall waterfall development model, which is a software development model from birth, from idea, through to rollout implementation within your system. And basically, we can see that the conceptual modeling maps onto some of the first steps, roughly. The logical stage roughly maps onto the design stage, and the physical design roughly matches onto the construction phase of the waterfall model. And one of the main aims of this first half of the lecture is to go through the waterfall model in a lot more detail. Okay. But first, before I do that, we talk about design. Well, what are we designing? Because there's lots of things that are involved in the design of a software system or a software system. So obviously this term this semester we've been concentrating on the data model, the underlying, how we structure the data in a database or in a database system. What are the entities of the system, the real world objects that we're trying to model, the data entities, how do we what's the appropriate spatial representation to use? These are all design decisions. What the attributes of the entities, the objects that you've defined are, what are the relationships and constraints exist between the entities, and another part of the data model that we're going to deal with next week is metadata. It's not actually integral to the data model, but it's very closely associated, should be closely associated with it. Not only do we have how we store and the relationships between the data items that we have in our database, we've got potentially we're designing system architectures being the various software components that we put together to create our overall system. We may be designing program logic, how we actually write programs to actually manipulate and change data ourselves, and we may be designing user interfaces to provide access, relatively straightforward access for different types of users to the underlying data in the system. So these are all things that are involved in design. Okay, development methodologies are formal approaches to developing software systems, including databases. Simple as that. So development methodology, formal way of doing things. And in the design lecture, I went through, we had those, I discussed some of the reasons why development methodologies were important. Certainly for developing large-scale corporate systems is where their efficiency grows. If it's just 2 people or 3 people who can sit around the table and things like that, a formal design methodology may help you structure your ideas and how you go about things, but clearly the more people involved, the more subcontractors, the more different roles are involved, the more important a structured development strategy is. They encompass both the design stages and the implementation stages, processes, and how do these models differ? Well, development methodologies differ. They differ in the stages that are described and the order in which those stages are undertaken and what is emphasized in the various stages of the development methodologies. And as I think we saw from the previous few lectures ago, that certainly not following a design methodology increases the risk to complex software systems and is believed to can have a significant effect or influence on success or failure of a system. So, the waterfall model is our first design methodology that we'll look at. It's a simple linear model from requirements. So we have an idea. We decide, look into what the requirements of the system, what do we want this system to do. We decide whether it's feasible. Presuming it is feasible, we move on to the design side, the paper-based modeling side. What do we want it to look like? What do we want it to do? How is it going to do this? How are we going to structure the system so it can deliver what we want? Then we build the system, test it, implement it, and review. And we'll go through this in due course. But I'm just going to show you a few different design methodologies before going through the waterfall model in detail. So the waterfall model was, to a certain extent, the very first well, it was the very first design methodology, and it was, as I think I mentioned, it was derived from methodologies, approaches used to design manufacturing product lines and things like that. But it was soon recognized that the linear start idea, work your way slowly through to the end product, finish model was not really very realistic when it came to software design. Might work fine for basic manufacturing systems, which are mostly linear, but not for coding, developing software systems, which are far more complicated and involve far more, well, they're just more complicated. So one of the issues raised with the waterfall model was the lack of any feedback in the model. You started at the beginning, you did step 1, then you moved on to step 2, and you moved on to step 3, etc., all the way through to the end. And the reality was that, that there is feedback between all levels, potentially feedback at all levels at all stages. So here's just two different diagrams illustrating the feedback. Now you'll see waterfall models. Now the boxes, there are, a million. There are an awful lot of variants of the waterfall model which have boxes that are labeled roughly the same, slightly different numbers of boxes, slightly different titles. We don't worry about those details here. Just bear that in mind, that when I show you a waterfall model, you may see different numbers of boxes with different numbers of things, but the important thing is it's basically a chain of events. And we can see in this diagram, this is emphasizing the sort of short-term feedbacks between individual stages. So you do some coding, you learn something about the software libraries that you're using, maybe that information feeds back into the design so you can improve the design on relatively short time periods. But there is also feedback over longer time periods, so that once we've got a system operational and running, then the users can feedback further information, further requirements for the system to begin the whole system again, right from the beginning, or possibly if it's a small change, it could come further lower down in the chain, or further down in the chain. So there is feedback both between individual boxes and across the entire system potentially. Here's an alternative or a development of the V model. Sorry, it's a development of the waterfall model called the V model, V for verification or validation. It is still a linear model. So this is sort of the linear part of the model here, this side here. And we can see we can develop the user requirements. We have a software requirement specification, high-level design, conceptual design, logical design, detailed design, then the actual coding side of it. So it's only got this diagram only has a smaller component of the entire waterfall model previously specified. But how does this differ? Well, what it has is for each stage in your model, you have a formal testing process to make sure that you have what you have done has met the requirements of the modeling methodology, of the design methodology. So, so when you write your user requirement document, some kind of the specification for the system, that has to be signed off by all those stakeholders who have been given, to a certain extent, a foot in the door, have a voice around the table. So you have to have it formally signed off. Down at the bottom level, so detailed design. So detailed design is the actual, maybe the queries in SQL, maybe functions written in JavaScript or some other programming language that together are put together to create the full system. And unit testing is basically saying a set of tests that you set up to test whether a particular small bit of code or function is behaving as expected. You think of all the possibilities that, say, for example, you could throw in a maybe it's meant to take an integer number. Well, what happens if you throw a real number at it? What happens if you throw text at it? What happens if you put in a very large number, a very small number? Basically, the software developers come up with a set of sort of stress tests that they can automatically run on the code, and it tests all these possibilities to see how resilient the bit of code is at that level. So what goes on at these levels, I'm not quite sure. It doesn't really matter. You can look up these details if you want. But basically, you have a formal testing signing off stage at the different steps in your model. And of course, verification, signing off, certification is important in the larger the organization is. So that's example of a V model. So two things that the waterfall misses out: feedback and checking that you're actually doing what you should be doing, and that people are agreeing that you're doing what you should be doing along the way. Now, 1970. A lot of things happened in the late 60s, early 70s in computer science. A lot of the basic, a lot of the ideas that we use today were invented then, including the idea of the agile development movement. And I'm not going to go into any details of it, but I want you just to sort of know and understand what agile is. So this was a criticism of the sequential development model, and one of the particular criticisms was, how do you know up front what you want at the end of the day? It's a learning process. As users, particularly early in compute, when people are not familiar with computing, people didn't have computers in their homes. That was unknown until the sort of early 80s. So people aren't familiar with what computers aren't necessarily even were, never mind what they could possibly do. So how do you decide up front what your system's going to do when your learners don't really understand what the potential of the system might be, and I hasten to say its limitations. So it's easier for users to determine system requirements as a reaction to actually having something to play with, something physical to see, to manipulate with, to experiment with. So the basic principle is to have regular, they tend to call them sprints, which is not a very friendly term, or iterations, at the end of which the teams must present a potentially shippable product. This is a sort of modern version of Agile, I hasten to say, rather than 1970s. So basically, the team builds a mini working system, or a system that does implements a certain amount of functionality, but potentially is a usable piece of software in its own right, and then the users experience that, then that feedbacks to their ideas of what the system might be able to do, how they might be able to use the system. So if you follow the waterfall model, the development teams only have one chance to get every aspect of the project right. If you follow an agile paradigm, you're constantly re-evaluating what you're doing and why you're doing it. And when I say constantly, I mean cyclically. You decide, you evaluate, you implement, you test, examine, then you have another iteration, another set of requirements established. So it's not that you're constantly every minute revising your things. It's every week, every month, depending on the cycle speed. Agile itself is not a methodology, but it's a kind of approach to software development that is then implemented in various formal methodologies, the most common of which is called Scrum. And there's the end of my knowledge on the agile development movement. Okay, but core to agile is the concept of iterative development, and indeed to other models, software development models as well. And that is the fact that you develop software not through deciding exactly where you're going, but by experimentation, by slow development. So you have a system whereby you start off with a design phase, come up with a basic system, or a system design, and initially it would be, say, implement one component of a large software system, potentially. Then you build the thing and test it. You learn about it in the lab. So these are the programmers, the programming team, not necessarily the user team, doing the testing, the prototype in the lab, developing and testing in the lab. Tidy it up, make it usable, make it robust, so that you can then send it out to the user community to test it, learn about it, and it can be evaluated because it's reasonably robust. Remember, we're making effectively a working system, a little mini working system. We can send that out to users. We don't have to have a technician standing over them, making sure the thing doesn't fall over. I mean, when you start writing software, you'll soon realize how it's quite a big job to remove all the bugs out of potential bugs out of software programs. So you make it sort of reasonably shippable, give it out to your users. The users play with it, experiment. They feed that into the next design loop. Spiral models. Okay, so the spiral model is an iterative model with a formal risk assessment after each iteration, as part of each iteration. So basically you come up with a design. I think we start in the middle of this one, so we start in the beginning where it actually says review, but I guess this is how I've been reading it. You take it first thing you do before you actually start building anything is to have a risk analysis. What things might go wrong? What things, do we have the right resources? Do we have the right personnel, software, soft knowledge, programming skills, etc., etc. You develop a prototype, etc., etc. You go round our iterative cycle. Before we start on the next one, we come up with the next design here, the second prototype design, formal risk analysis, blah, blah, blah. So that's really all I'm saying on that. Basically, risk analysis is important, especially in large software systems where things can go very wrong. So that's a third thing. So we've got iteration, we've got risk. Okay, so that's really all the different software methodologies are. I believe there's hundreds, or at least tens, if not hundreds of these software development methodologies out there. This is not, whole courses are taught in the SB building on design methodologies, and if you want to know the details of, more details on design methodologies, that's the sort of place you want to go. Anyway, here is an example of the waterfall model. So what I'll go in before we have our break is just run through this quickly in a bit more detail. And as you can see, it's yet another design approach to the or version of the waterfall model. So we start up at the top with database planning. This is a particular one that's obviously aligned to database development as opposed to general software development. So the first thing you do and this will be I'll talk about this from a sort of corporate perspective, is first of all you want to identify what's presently going on. What are the existing systems? What are their strengths? What are their weaknesses with regard to delivering business needs? At this point, it's a good idea to consider what standards, if any, are being used across the existing systems. Are any standards being evolved? Remember standards, the postal address format, OGC simple features, metadata standards. There are lots and lots of standards, both for software and for data. So look at what existing what standards are being used, and also what standards exist in the domain area. So since the last software system was built in the 1970s, have new standards been agreed by various organizations that you want to start to bring into your system? And the other big part of it is what's called a feasibility study, which is basically asking the question, is it doable? Is it possible? Can we do this? And again, each waterfall model has different lists of feasibility. There's whole books written on feasibility analysis, but basically we can divide them into a number of different questions that we can ask regarding feasibility. Technology, do we have the technical skills and resources to build it? Or have we got to bring new staff in, or do we want to outsource it to a development corporation, a software development company? Do we want to build it in-house? What are the options? Or a mixture of both. Sometimes you have in-house people, but you also bring in experts from outside, and then it becomes a learning process for the in-house staff. So you can get benefits by outsourcing or having a mixed strategy for software development. Economic, will the benefits outweigh the cost of the system? Obviously, developing large, complex corporate systems is very, very expensive. What will it actually be worth the effort? Legal. Are there any legal constraints on the system design? So there may be Data Protection Act in the United Kingdom, for example, which prevents companies giving out personal information when it comes to individuals. There are also legal perspectives, for example, for legal reporting to government and things like that. So you may need the system to meet your legal obligations, perhaps as a mining company or something like that, reporting pollution, reporting things to the government, to other organisations. Operational, just simple, will the system designed actually meet the business needs? Now, you can say that that was should be part of the requirements analysis, and indeed I find quite a lot of these things sort of repeat themselves to a certain degree through the system, but I think there's no harm in having one person write, or one group write the specification, and then another group check that it's actually meeting the business requirements. Remember the V model, this fact that you're checking what you're going as you're along. So would it be provide the functionality? Would it be reliable enough? Systems that aren't reliable aren't necessarily a good, aren't very useful potentially. How easy is it to maintain? After all, these systems, especially if you're investing millions, tens of millions, hundreds of millions of pounds in software systems, you want it to be reliable and maintainable. Is it going to be easily usable? There's no point in building a giant whiz-bang, all singing, all dancing system if it's not actually very usable. Dare I say, think ArcGIS there. Although that's not the worst by any means, but I'm sure you've had usability issues with ArcGIS, and if you haven't, then you're a lucky soul and you will have. So, and indeed all software is that like. Sustainability, affordability, blah, blah, blah. And scheduling. You know, there's no point in building a system if it's not going to be ready in time, or it's going to take too long to build. So, whole variety of list of things to discover to decide whether the design that you've come up with, or let's say the system, the conceptual model, is feasible for an organisation. So the next box on here is called system definition, and as I say, I find there's quite a lot of crossover between these stages at the top, and on many of these waterfalls, of course, they're collapsed into a single stage. But anyway, so system definition, under this we've got the identification, the business scope of the database application. Not 100% certain how that differs from the database planning stage, but so you need to know, I suppose it's doing things like potentially like which departments in an organisation are you going to have to gather data from and things like that. You identify the various user groups where the software is going to be used in the organisation, and how the system that you're intending to build fits into existing other software systems in the organisation. Is it going to be a direct connection, a periodic connection, data upload, exchange, if you need different database systems to talk to each other? So that's the system definition, and as I say, I'm not convinced there's a great deal of difference. Okay, between the top two. So the requirements collection and analysis is, I think, going into more detail on So basically up here you have an overview, and then you're, as with the logic, the conceptual, the logical, you're getting more detail as you go down the system, down the sequence. So the requirements stage, we've got collecting and analysing information about the organisation. So this means actually finding out what data. So one thing is knowing that there's a data set held by the accounts department or held by the roads department if you're in a council. So there's one thing about knowing it, which is kind of the stage you're at up at the top. This is about actually getting the details about what that data is. Where is it stored? How is it formatted? Is it documented? All that kind of stuff. So this is getting to the actual detail, the atomic level of where the data is. Again, refining user requirements. You're always refining. You start with a big, broad picture. You start focusing in more and more about what individuals want. So at the top level, we're talking about what the managers want, usually. You're talking about strategy across an organisation. By this stage, we're talking about the person who's working on the checkout, at the end of the phone, ordering you a taxi, working out where your Yodel parcel is, whether it's in the bush down the road or whether it's in the river down the road. So those are sort of burying down to those individual user requirements. What actually coming in and saying, well, what actual software and hardware do we need to run this system that we're proposing on? Finding out whether the information, once you've collected and analysed the information about the organisation, is it all there? Or have you actually got to create new data, create new information to be able to implement this stuff? And if it doesn't, do you have a system? Is it possible to actually find the bits that you don't need? Database design, well, we know this, we've done this is what we spent most of our time on, or a lot of our time on, is the development of a design to support the organisation's operations and objectives. We've seen that this includes the logical design using ER diagrams, UML diagrams, if we're an object-based approach, and also the physical design of the system, which involves two things. First of all, deciding what software you're actually saying we're going to go with this software, this DBMS, Database Management System, and then we actually implement the logical model in the physical model. So we'll just join that side box for a moment. How do you go about selecting a database management system, or indeed any other software system? Well, clearly you have to consider the underlying database model. We've got these different database models, which is the most appropriate. You have to consider the functionality of the software, and that's bearing in mind not only what the software itself as it comes out the box or installs off the MSI file, the installation file is, but also all the add-ons, additions that may be developed by the community or may be sold by third-party developers and things like that. And the functions you may be interested in is not just, when it comes to databases, the core database functionality. You may be interested in, does it support graphical user interface development? So Postgres comes as a vanilla database. If you want to build an interface onto it, you have to do it in some other programming system. It doesn't get shipped with an interface building system. Oracle, probably the world's largest commercial relational database, comes with a whole suite of form development software that allows you to write and develop form-based interfaces onto the Oracle databases, graphical user interfaces onto them. So it comes shipped with all that. That's one of the things you get extra. Also things like help wizards, okay? The functionality might be there, but how easy is it for users to use? Have you got to be a command line wizard, or are there point and click wizards that allow medium level users perhaps and lower level users to undertake things that would otherwise have to be done by people with more programming skills. Obviously, performance is one of the things we also need to consider. Obviously, cost. So I think we'll have, next year we'll think about open source versus commercial software. You probably covered a little bit of that already. Obviously, there's purchasing costs of software. Something like Oracle 8i, hate to think how much one license of Oracle 8i costs, probably a few £1,000s at least, versus Postgres. We can download, we can get going immediately, so it's free. But there's not just the cost of the purchase of the software, obviously, there's lots of other costs as well. There's the cost of the implementation costs of open source are generally much higher. So you win on the off the shelf price as it's free, but then you've got to have a higher level of skills to actually use and develop with that software often than you do with things like Oracle. There's a lot more support for Oracle. Certainly when it comes to open source information, that things like the help facilities and things like that are liable to be a lot worse than with commercial software. So how skilled is your workforce? Are they the kind of workforce that can handle the open source environment? Is that the ethos of your company that you're working in? Or are you more of a sort of traditional corporate environment where we want where safety and reliability is more important than perhaps innovation? Portability, so we live increasingly in environments with mixed Linux, Apple, Windows operating systems. This used to be a real barrier to software development. I think in the last 10, 15 years, the ability of different operating systems and hardware and software operating systems to talk to each other is much less of a problem than it used to be. But it is still an issue. Network speeds, things like that. Do you have a speed, is your network suitably powered that it allows you to actually distribute the data across it? A lot of the times when you decide about what software system to use, you may undertake some kind of benchmarking exercise. And a benchmarking exercise is simply a formal testing or comparison of all alternative solutions, software solutions. Now, in principle, benchmarking is a very sensible idea. The reality of benchmarking is far more complicated, and it's very difficult quite often. It's quite often difficult to get equivalent hardware, software systems to get equivalent testing. So, of course, how system software operates depends on how the hardware is set up. So one software system may work faster on this architecture than its rival, but on the other architecture, the other one works faster. So unless you test both those architectures, you're not going to know the relative differences between them on the different architectures. So you need to try and compare software running on identical or at least as equivalent as possible systems, which is often not possible. So for example, ArcGIS only runs on Windows. You can't test it on Linux. So if you're testing a Linux-only software against a Windows software, it's difficult to do. Direct comparison. Two types of benchmarking. There's the quantitative benchmarking, real figures. How quickly does this query run? Does this query take to run? Very simple, you've got real figures. But there's also a qualitative benchmarking, things like how easy is the system to use, how good's the documentation, and things like that. So any benchmarking exercise will be a product of both qualitative and quantitative assessment. This is quite a nice, easy read. It's a bit old and fuzzy, the scan that's available, but it's a good basic introduction to software benchmarking and some of the issues, database benchmarking, some of the issues that surround it. Application design. So we've selected our database. We've now actually implemented our basic database. We've implemented our structure, our database schema. So then we move over to the applications. Now, the applications are the software that users, or most users, use to interact with the database, in this case, the database. These are often graphical user interfaces, but they may also be command line interfaces like pgadmin3 and things like that. So obviously we're going to meet GUIs next year in quite a bit more detail, but just as a quick introduction. So when you're thinking about GUI design, graphical user interface design, the things to think about, the principles are how to structure the fields and the other bits of information that you're displaying on your graphical user interface. General principle of simplicity, keep things as simple as possible. This is generally a good principle in life, I think, never mind software design, cartography, just about everything. Simplicity is generally a good idea. What things are visible to who, how users get feedback, if they want to know, if they want help, is there sort of tooltip help, all that kind of stuff. So you hover over what the tool that you're interested in, does it pop up with a help box? Do people have to search through some sort of help system? Is it searchable, or is it just a sort of PDF document people have to move through? How tolerant the system is to somebody clicking 20 times on a button while they're waiting for it to do something, so a degree of robustness of it. Practically, so that's the sort of principles that you need to think about, but practically you need to think about meaningful titles for systems and menus. Don't have, use sensible words, comprehensible instructions that are suitable for the level of the person using the software system, logical grouping and sequencing of fields, visually appealing, intuitive, consistency of terminology, use of abbreviations. Generally, it's a good idea to avoid using abbreviations unless they are integral to what people are doing, suitable use of color, etc., etc. So you're designing your applications. Here we've got a prototyping stage linked to our application design. So we're using an iterative prototyping approach in this case to develop these applications. So we've met this already. A prototype is just a working model of some or all of the, in this case, database application. What's its purpose? Well, to identify problems, but also help users clarify system requirements and possibilities. Yeah, that's just a diagram. Yeah, I mean, that's pretty self-evident. Use tests. Okay, implementation. So we finally got to an implementation stage. This is the physical, so you've effectively decided what you're building, and you've built it, just about. So what do? You need to, it's always a good idea to test the system. You need to test the system before you roll it out to your big user base, which may be thousands of people. And if it fails, potentially your company loses thousands and thousands of pounds, you lose your job, millions of pounds, you lose your job. So it's important that this is done right. So it's often a good idea, in fact it's always a good idea, to load a subset of the available data in. Some data loading into large systems can take days. It can be a hugely complicated undertaking, and I'll talk about, to a certain extent, we'll touch on that next week when we look at data warehousing and data mining software and applications. But it's always a good idea to load a subset into the data. So many times I've loaded all my data up, discovered I've made a fundamental error, throw it all away, start again. So nice subset of data. It also means everything takes a lot less time to do the tests that you need to do. I could do a test analysis on the entire of the UK, or I could just do one county of the UK. It would take a fraction of the time. As long as the data is equivalent, it's just size-wise it differs. At least I can test the software suitably. Obviously allows, again, another case to model. Existing clients. Okay, so the application design was designing new clients to plug into the database in this case, but often there are legacy client applications that maybe looked at a previous older version of a database, or that you want to expand to add in some of the data from the database that you're implementing. So you may need to modify these existing applications to deal with the new database structure. This is also the point at which user training generally should be started. So it's a good idea to have 6 months or so before you roll out a system into the general organization to have training sessions for users so that they start to begin to get familiar with the software, get used to it, and start learning. I also say at this point, this is a good point actually, in the implementation, to sort of identify champions, people who are interested in the system, and therefore, and they can be at any level from sort of people who are effectively clerks up until senior managers, but people who show an interest at a particular level in your organization, in the software, in using it, and they're often very useful because they can they learn a lot more, and then they pass their skills on to their colleagues round about you. And indeed, that's how I, to a certain extent, started my GIS career, was by simply being interested within an organisation that was implementing a corporate GIS system. Okay. Finally, we're getting ready to actually get the system running. So the transfer of existing data, or transfer of data into this system. You probably got, nowadays, there's almost certainly existing digital data, certainly in this country, but there are still probably cases in the UK. In fact, I'm sure there are in the UK, especially with smaller organisations, which are still digitising paper records. And when I started the GIS, in the GIS, that was what we were doing. We were digitising paper, sepia film records. That was our main task. We didn't have existing digital data for, in that case, the water mains of Edinburgh. Of course, in many places around the world, developing countries, digitisation is much further behind, and this is a much more important and vital part of the process. Not only do you have to get the data in, you have to check that it's in correctly. And this is, again, quite a complicated process and long-winded process. How do you actually check that the data is loaded correctly? How do you quality assure the data? Okay, you might get an automatic data load, may kick out some data load errors, and you get an error file that says this record didn't load for whatever. But there may be errors in your transfer load algorithms that's preventing data to load up as well. And you also maybe want to think about some sort of quality assurance for the GUIs that you've developed. Are they actually delivering what you need? So basically, load your data, check that it's loaded correctly. Evaluation. So you're now up and running. You've got your corporate system up and running. You should now evaluate what's actually happened. Has it been a success? Survey users to determine satisfaction, and then perhaps you want to decide you need to improve documentation, improve training, add new training, maybe change the application design. Of course, we go potentially going back to the beginning in our system there. So evaluate the system. And then the final thing is to keep it running. And we've got two types of or a number of different types of maintenance that we need to consider. Preventative and corrective maintenance, which is basically backup and recovery. The last thing you want to do is to lose all your organization's data somewhere, so make sure you've got backups, regular backups, make sure you've got backups in suitable locations. So it's not only that you have at least one backup in the same room that your main server is. Obviously, there's off-site backups, so in case the building burns down, lots of options like that, multiple copies, etc., etc. Then there's adaptive maintenance. All systems change as they're used. More and more users come on board, potentially. More data goes into the system. So what worked and functioned perfectly well 10 years ago might be starting to grind to a halt after all the software, hardware is starting to get a bit old. So you need to undertake potentially performance audits of the system. How well is the system running? Is it meeting the requirements of our organization? For example, eBay and Amazon. If you have to wait a long period, even a few seconds, for a sale to go through the system, you're potentially losing customers through the system. So it's very important that you meet performance targets. And of course, security as well. Security is a constantly changing situation. Holes are always being found in software systems and in complex, corporate, heterogeneous, complex, large corporate systems. There could be many, many potential holes. So you need proper security for your system. I think we'll just do the roles and then we'll have our break shortly, because I think there's just 2 slides on that. Probably the most important person when it comes to database management is your database administrator. And any most reasonably sized organizations that have large databases will have database administrators, 1 or more of them, depending on how many databases they have, etc., etc. And they're basically responsible for the management of the data resource and the application itself. They're the overall person responsible for that system. So they're effectively a manager. They manage the planning and development, the conceptual, logical design, physical design, the entire system, and make sure that the system meets the requirements and that these various steps are suitably implemented. Who are they implemented by? Well, a whole variety of people who have a whole variety of job titles depending on what organization you are. But just broadly, you can, at a very broad brush level, you may see jobs advertised like this. So if you're going into a sort of applying for sort of more technically based GIS jobs, you may see jobs that are not actually described as GIS person, GIS technician, GIS analyst, or anything like that. But you might see things like system modelers who are responsible for communicating with users, specialize in the soft side of communicating with users and putting together user requirements and the conceptual designs. They may be often called system modelers. Then you have database designers. They're your hardcore SQL people, doing the database schema, implementing the constraints. That's something you've been doing. You've been database designers for the last few weeks. Security constraints, so hard stuff. Then you've got potentially application programmers who are writing the applications that plug into the databases. I mean, in a small environment, a simple system, the database designer and the application programmer might be one job. But in many organizations where specialist knowledge is required for each of the different knowledge is required for application programming, JavaScript, HTML, CSS, if you're in a web development, maybe C++. It's more of a programming role as opposed to a database designer role. Oh, and then you've got all these end users. Okay, so you've got your naive users, unaware of the DBMS and the database. They simply use point and click and away they go, such as a checkout operator. Then, more importantly, or more, well, it's not importantly. That's the wrong word. These are very important people. But from more interesting, I think is a better word, maybe, or maybe. But sophisticated super users who are familiar with the DBMS and can design their own applications. So these would be, you know, we want somebody who's a town planner with an expertise in GIS, so to speak. And as I say here, it's good to identify these champions, people who are willing to go the extra mile to help the system implementation, to communicate with their colleagues, to you know, champion the system so that yeah. Okay, let's have a break before going on to